In this video, we are going to review the subatomic view of particles as well as explore what are quarks and why quarks are so important. So let's start off with a little review of subatomic particles. Once we learn more about quarks, this chart will be revisited later in the video. But let's start off with what we know. There are two types of subatomic particles. We have big particles, which are hadrons, and we have small particles, which are leptons. Now, hadrons can be divided into two other particles. We have something called mesons, which is the Greek word for middle. And then we have something called baryons, which is the Greek word for heavy. Baryons are heavy because they contain something called 3 quarks. They have either 3 quarks or 3 antiquarks. Whereas mesons are middle, meaning they're not quite as heavy because they only contain 2 quarks. And they must always contain a quark and an antiquark. Now mesons also have different spin. Okay, so mesons are something called bosons because their spin are full integer spins. Whereas both baryons and leptons are fermions because they have half integer spins. Now mesons are also called mediating particles. So some examples of mediating particles that are mesons are pions, kaons, upsilons, and psi. Whereas examples of baryons are neutrons, protons, omega, sigma, and lambda. Now some examples of leptons are going to be electrons, muon, muon neutrino, tau, and tau neutrino. So the particles which are fundamental are going to end up being leptons and quarks. Because if we look at this here, mesons and baryons are made up of quarks. So that means mesons and baryons, or hadrons, cannot be fundamental particles. And leptons, these are fundamental particles because they can't be broken down any farther. So what are quarks? Well, quarks were first hypothesized by a scientist named Murray Gell-Mann. He came up with the idea that there were 3 quarks: an up quark, a down quark, and a strange quark, along with their antiquarks. Now, let's think about this. If there are 3 quarks that make up a proton, and a proton has a charge of 1, how can these quarks have whole integer charges? Instead, he said that the quarks must have fractional charges. Even if we look at a neutron, there are 3 charges which make up a neutron, or 3 quarks. So these quarks have to somehow add together to get a 0. Well, it turns out that quarks either have a 1/3 charge of an electron or a 2/3 charge of a proton. Now, these quarks were all just theory by Murray Gell-Mann until 1967, when a group of scientists used accelerators to shoot electrons at protons. The scattering of this collision produced something very similar to Rutherford's gold foil experiment with alpha particles. And the scattering suggests that there were 3 concentrated centers within a proton. Later on, the same was done to a neutron. So let's look at these fundamental particles that make up protons and neutrons and how they kind of work and how their charges work together. So let's first look at a proton. So if I have a proton here, we said they're made up of 3 quarks. Well, we're going to look at an up quark and an up quark, and then we're going to have a down quark. Now, up quarks are going to have a 2/3 charge. A down quark is going to have a negative 1/3 charge. Because remember, the negative charge is 1/3 of an electron, whereas the up quark, which is a positive charge, is going to be 2/3 of a proton. If I look at these and I add these together, I'm going to end up with 2/3 plus 2/3 minus 1/3. When we combine these, that's the same as 4/3 minus 1/3, which is plus 1. So my charge of the proton is plus 1. Now, let's take a look at a neutron. Now, a neutron is made up of 2 down quarks and an up quark. In this case, we're having 1/3 negative plus 1/3, and that's a negative, and then we're going to be plus 2/3. Now, altogether, we have 2/3 negative minus 2/3. This gives me a neutral charge. Now, these charges in a neutron help scientists explain why sometimes a neutron acts like it's charged. Now the proton and neutron explain two quarks, the up and the down quark. But as some of you remember, Murray-Gell-Mann predicted three quarks at first. So what is this third quark? Well, this third quark is called the strange quark. Now you may be asking, why do they call it the strange quark? Like, that's a strange name. Well, that's because it was observed in the interactions of three particles that interacted very strangely. These are the lambda, sigma, and kaon particles. So these particles would decay and interact in very peculiar ways, and when they decayed, we noticed, or when they interact, we noticed this strange particle and how long it lasted. And that's why it's called the strange quark. Believe it or not, quarks help us understand beta decay a lot more. So let's first look at a beta negative decay, where a neutron turns into a proton. So here, a neutron has two down quarks, so we have a down and an up quark. Now, one of these down quarks is going to change into an up quark to become a proton. So now we're going to have a down, up, up. If we look at this here, we have a charge of 0 on this side and a charge of +1 on this side. And what is released is, we find out, an electron with a -1 charge and an antineutrino. This satisfies all the rules we learned about beta decay before. Our charge on the parent side is equal to 0. Now our charge on the daughter side is equal to the proton, which is +1, added to the electron, which is -1, which equals 0 as well. So my charge is conserved. On my parent side, I have 1 baryon. On my daughter side, or the product side, I have 1 baryon. Now on the parent side, I have 0 leptons. On the daughter side, I also have a net of 0 leptons because I have matter and an antimatter for a lepton, so that means we have a net of 0 leptons. Now if we didn't put the antineutrino there, then we would have 1 lepton, and that would make it imbalanced. Now this electron and the antineutrino electron represent something called the weak nuclear force, which symbol in this case would be W negative. The electron and the antineutrino electron are the mediating particles of this weak nuclear force that is responsible for changing one of these down quarks into an up quark. So when we are changing an up quark to a down quark, which is beta positive decay, we are then having a positron and a neutrino, because a positron is a lepton that is an antiparticle, whereas a neutrino is just a regular lepton. So in other words, when we have an up quark that changes to a down quark, we end up releasing a positron and a neutrino. And these here will produce my weak force. Whereas in this case, we use a positive donation to donate the weak force, since we're using a positron. But wait, some of you might have heard that there are 6 quarks, and so far we have only learnt of 3 quarks. We have learnt of the up quark, the down quark, and the strange. So what are the other 3 quarks? Well, in 1974, they discovered the charm quark, which was previously predicted, so it wasn't a big surprise. But then they started thinking, wait, if there are 6 leptons, shouldn't there be 6 quarks, the other part of our fundamental particles? And that turned out to be true. There is also top quark and a bottom. The main ones that we really have to know about in this class are the up and down quarks and how they interact. Now you may be wondering, how do these quarks stay together? Like, that has to be a pretty strong force, since it's super hard to break apart a proton or a neutron. And we also might be thinking, hey, well, we've heard of the strong force, maybe the strong force applies to this. Well, yes it does, and quarks and the forces that hold these quarks together actually help us understand this strong nuclear force which keeps together our nucleus. Basically, the forces that hold these quarks together are 3 charges, and we donate them as colors: red, green, and blue. But strangely, these colors have nothing to do with the color of these charges. We just gave them these color charges because all the other ways of describing forces were used up, such as positive and negative. And there are, in fact, three different charges here, so we needed a group of three, and the simplest way to do it was we gave them names of colors, red, green, and blue. So cool, we learned there are three colors that are responsible for the nuclear strong force and holding all of these tiny particles together. But now, how do they work? Well, first of all, we have to understand that each color has an anticolor, like how each particle has an antiparticle. Another thing that we have to understand is that just like how a negative and a positive charge with electric charges, opposite color charges attract, which means red, green, and blue are all attracted to each other. Now, another weird thing that happens here is that as we pull the quarks apart, the strength of these color charges increases. So the attraction increases when we pull them apart. Now this attraction that increases when we pull them apart can be explained by gluons. So what is a gluon? A gluon you might think of as the glue that holds everything together. A gluon is a mediating particle made up of two color charges. Always a color and an anticolor. Now, it's not going to be a color and its anticolor, it's going to be one color and a different anticolor. So the anticolor for red will not be combined with red, it may be combined with green or blue. Same like the anticolor for green will be combined with red or blue and not green. So a gluon is just made up of two color charges. Now, these gluons are constantly interacting between. Now we call these gluon mediating. Now these gluons are called mediating particles because they're constantly interacting between the quarks. So now that we know what a gluon is and what a color charge is, we're going to apply these to quarks, which have color charges. And remember, a gluon is a color and an anticolor. And why we call these gluons mediating particles or exchange particles. Now this is where things get very interesting. It turns out that color charges exchange gluons. And we know quarks have a color charge to them. So if I look at this down charge here, which is red, it's going to maybe shoot out a gluon to exchange with the blue one. So let's say this red quark here, this down, produces a gluon and exchanges it with the blue quark that is a red and an anti-blue. Now when the blue quark accepts this gluon, this quark here is now going to change color because the anti-blue and blue are going to react, changing this color to maybe red. So now let's pretend at the same time this green quark, which is an up, shoots out a blue and an anti-red to my other red down quark. So this ends up, the red and anti-red are going to interact with each other, changing maybe this quark here to a blue. So that kind of shows how the quarks are constantly exchanging gluons with each other because they have color charges. And particles with color charges will exchange gluons, which is a color and an anticolor. Thus, the quarks are in fact themselves changing each other's color as they interact with each other through the exchange of gluons. While these exchange of gluons are happening and our quarks are constantly changing colors, it is important to notice that the net charge must always be zero. So that means we must always have an equal amount of green, red, and blue quarks. Another thing to notice is that the color charges don't actually interfere at all with the electrical charges of the quark. So the up quark still remains an up quark at 2/3 positive electron charges, whereas the down quark still stays the same as negative 1/3 or a third of an electron charge. So this helps explain why the strong force is constantly occurring and how it's so strong. You have these quarks producing gluons, which have a color and an anticolor, which reacts with another quark. And remember how we have antiparticles and a particle, when they collide, it's pure energy. Well, same thing here. We have energies reacting with each other, wiping each other out, which is creating energy. Now, an interesting thing is a gluon could split into two quarks, while two gluons can also make a quark. So we're constantly, even though we draw always three quarks, because the net is three quarks, we're constantly creating and losing quarks all the time with the gluons. But for simplicity terms, we just say there's 3 quarks. Now another interesting thing is, since we know that a gluon could separate into 2 quarks, maybe a quark and an antiquark, so then how does this affect the nucleus and the strong force of the nucleus, these color charges and quarks? Well, we just talked about how quarks could combine to produce a gluon, and how gluons can separate to produce 2 quarks. So let's say this down charge here produced a gluon, and the gluon separated into 2 quarks. So now these 2 new quarks are going to interact with the quarks on this proton, causing these 2 quarks here to annihilate each other because it's a particle and an antiparticle, which leaves us with still 3 quarks, but it had also affected the color. So constantly there's a quantum state happening here where this down is green but blue, but it could also be red. It's constantly in flux of its color. And that is why the strong force between not just quarks within a proton, but between neutrons and protons and protons and protons and neutrons is related to quarks and color charge. So I'm going to leave you today with this concept map that I have started for you to finish off. So I want you to find the connecting words and expand on this mini concept map of fundamental particles and forces to show me your understanding of what you have learned today.